All right, so we are going to continue from where we left off. I couldn't join you for the in-person class on Friday, but I have a sense of what you did and um, a few of the things that you covered. So today we are going to make progress from that end and move into some interesting things that we can do with respect to what you covered. Um, okay, so quickly, I'll share my screen with you so that we'll start right away. Okay. Oh. Okay, so based on our schedule, um, there are some few things we have left hanging a little bit, and that's because we want to understand some things before we come back to this. So, for instance, hyperparameter tuning and techniques, we'll come back to that. But because you started with the theoretical concept of um, classification algorithms, I would want us to continue from that point. So today we are going to look at decision tree development, and decision tree is an algorithm we can use for both classification and regression. Now, what I intend to do today is we are going to look at the theoretical foundation, and then we will look also at the mathematical foundation. Now, it is an algorithm, so I always tell students algorithms have their theoretical foundations, and once you get that theoretical foundation right, it sets you on a good path. So what I'm going to do is I have this that I'm going to share with you, but then I also have this, and let's quickly just move on to this and see what we have over here. So today we are going to look at decision trees, and with decision tree, it is a very popular machine learning algorithm that has a lot of use cases and applications. And with that out of the way, now let's look at what we are going to look at today. Today we are going to look at this is a presentation outline. We are going to look at the introduction, some theoretical foundation of decision tree algorithm, the mathematical foundation, and then we are going to see how we build machine learning models using this algorithm called decision tree. So a decision tree classifier is an algorithm that uses a tree-like structure to classify instances based on their feature value. So yes, we would want to maybe classify students into males and females. We'd want to classify students into their various departments, and to even look at, more practical use cases of how decision tree works. Maybe we want to classify patients into some disease classification, okay, based on some data set that we have. So we are saying that the algorithm works like it has a tree-like structure where based on the features that we extract from the data set, we'll be able to do some calculations one way or the other. Now, the second point I have over here is decision trees are non-parametric supervised learning methods used for classification and regression. So they can be used for both classification and regression. And as we move along and we build some of these things, we are going to see. Now, the goal of decision tree basically is to create a model that predicts the value of a target variable by learning simple decision rules inferred from the data features. So the inherent data, we are going to learn or make some decision rules, and out of that, that algorithm will be breaking down like a tree. Now, the tree can be seen as a pairwise constant approximation, and there's a reference over here. Now, this reference will lead you specifically to the scikit-learn website where they have a little bit notes about the decision tree algorithm. So I purposely put out that reference there so that at least you can have time to read. It is quite a lot. Okay, so yes, we are going to use scikit-learn to build models. So they have some information over here you can spend time and read. But then let's proceed with our presentation. So at the end of the day, you see a lot of these images around, okay, and they are basically communicating the same concept, theoretical concept of decision tree. Now, what you see over here is we have nodes, and at the very top, we have probably what we can refer to as the root node or the mother node. And then it will degenerate or decompose into leaf nodes and some decision nodes. We are going to see what each and every node does at the end of the day. But over here, you could see that here, so there's a branch over here, and then there's a root node, as I earlier stated, and then there are some child nodes or some internal nodes, and there are some leaf nodes. The leaf nodes are the low-hanging fruits; those are just hanging, and then the child nodes, some of them we refer to them as decision nodes. We are going to see why they are called decision nodes and stuff like that. But then let's analyze this image briefly. And over here, we are trying to look at, okay, trying to predict whether it is going to rain or not. And based on the weather condition, we'd want to know if maybe, let's say, the football matches we watch on TV. Sometimes because of weather conditions, some matches are stopped because of maybe thunderstorms and stuff like that. Sometimes the weather is so bad that it is virtually unplayable in those conditions. So we are just assuming that use case or scenario. So the question is, yes, it is a tree. There are branches in there. So over here, it comes to the root node. We'll feed everything of our data here. And then we'll be asking basically questions. So is it sunny or the weather? Okay. If the weather is overcast, then at least it is a very, perfect condition to play. But then if it is sunny, then we ask the question of humidity. If the humidity is too high, you see that we have some decisions that have been made over here. And the blue ones over here are representing who play. And the red one over here is couldn't play. And over here, if the humidity is normal, high humidity basically means there's a lot of moisture in the environment. So probably there's a chance of rain falling. So you see that we making sense out of this. You see that the could play is there, and also there's a little bit of couldn't play because it can lead to rainfall or some unfavorable condition. And then we have the normal where we have couldn't play because the humidity is up there. Now we also have a condition where it is windy. So clearly, if it is true, then we see a lot of the couldn't play notes over here. And also if it is false, at least there's a little bit of could play. Now this may not make sense until we go on to the next slide where I have this interesting simulation over here. So over here, we are going to make decisions, and these decisions are going to form that tree. So at the very top, you are going to have a node like this, and this node is going to degenerate into the decision, yes or no, basically that. So yes or no will leave us with child nodes. So clearly you can see the child nodes over here. And depending on how the tree is structured and the tree is formed, which the next slide is going to help us understand that, we might also have other child nodes bearing fruit of or having nodes under them. So for instance, the one I have to my right has a child, but then the one I have to my left didn't have a child based on a decision that was made, which we are going to understand in the next slide. And then it can also degenerate, and for instance, this also degenerated into nodes. So at the end of the day, you realize that whilst we are making the decisions, some nodes will degenerate into having children, others will not. And the reason why others will and others will not lies in this. So at the end of the day, you see that I've highlighted these red nodes over here. And just by inspection, we see that these red nodes are the ones that give birth to other children, one way or the other. And we call these nodes, and also there are other nodes that are the blue ones we see over here. And these blue ones are basically not having children, one way or the other. So they terminate the branch of that tree in some regard. Now, at the end of the day, the red nodes are what we refer to as the decision nodes. So the decision node contains a condition to split the data. Remember, at the end of the day, the decision that we are making is based on the data that we have. So we are either splitting it or we are keeping it, basically. So the red ones are splitting it. And interestingly, the blue ones are more or less keeping it. And the blue ones, we call them the leaf nodes. They don't have children, or they don't split or degenerate into other children. Now, what they do is they help us in determining the class of a new data point. And this is very interesting. So the key thing I want you to keep note over here is, yes, we have the tree, but then it is important to know that we have the decision nodes and the leaf nodes. The decision nodes contains conditions that split the data. The leaf nodes will not split the data further. And the reason they will not split the data further, now let's look at this over here. And in here, I have some conditions over here. These are just on a high level, some conditions we can think of, okay? So on a high level, we have these conditions over here. And let's say x naught is less than or equal to 10. That's a condition this particular conditional node is given. Over here, this one is given x naught is less than 6. And over here, x naught is less than or equal to 4. All right. So now the point is the data is fed in. So we have this data set. And over here, we are doing classification, or the whole concept of whatever thing we are dealing with is classification. The reason why we are looking at classification is at least it makes the fundamental understanding right, and then we can move on to other things. All right, so there's label data basically. And the labels we have over here are these black labels and these purple ones, okay? So we feed this into, how do you call it? Let me just find my cursor. So we feed this into the root node, and based on the condition that we have here. Now this data, I'm just putting out these black and how do you call it, purple, just for illustration purposes, but this data will definitely be some numeric values that are going to be compared based on the condition we have over here. That's basically that. So based on the condition and the data that came in, this decision node did that computation based on this rule over here, and it was able to split the data. Now, after splitting the data, over here, let's pay attention. After splitting the data, we see that 5 data points goes to our left, and then the rest of everything minus this one goes to our right, based on what you are seeing. And then this one also is a decision. So definitely, it also has a decision to make. It goes through this decision as it has it over here, and then further splits this. And once the splitting is done, we see that we have this to our left and also this to our right. Now, one key thing we are beginning to observe over here is that because these are leaf nodes and they don't make decisions, you realize that there's only going to be a decision to be made if we have a mixture of things that we want to sort. Remember, the whole point is classifying. We want to group things into their proper class so that all the purples will move to one class and all the blacks will move to the other class. Over here, clearly you could see that from the node we see over here and with the data point that we see, or the members of this particular branch, there's no decision to be made basically. But when it's splitted and we go to this part, there was a decision because we still had some mixture of black and purple. Then if further down, after doing the splitting, you realize that, okay, there was some black over here and there was some purple over here. Then there were only purples over here. So over here too, there's no decision to be made. Now the point is, a decision tree algorithm, the whole theoretical concept is, it is always going to split until it is able to separate all the data points, like that we have the data points that only conforms to that particular rule that we have at that particular node. So over here too, we can clearly tell that yes, there's a decision to be made because we still have some mixture over here. So it goes through the process of checking this data point against these conditions. And it turned out that, okay, all the blacks are now here. And now we have the rest of the purples over here. So at the end of the day, we have this tree-like structure where the data set came in. And based on the conditions we have in the conditional nodes, we're able to do the splitting. And over here, this is just a binary thing. If it is a classification into 3 different classes, then there's going to be probably 3 different conditions that will be checked one way or the other. Okay, so at the end of the day, now let's go to a little bit of the mathematical foundation before we move into building the algorithm, because not building, but then using the algorithm basically. So over here, we can see that yes, the data set comes in, but then there's an interesting question I have over here. And the question is, okay, so we have 2 splits over here. The first one is what we see over here. Okay, so this node, for instance, has some mixture of black and purple on the left side. And on the right side, it also has some mixture of black and purple. All right. In the second split, we can see that, okay, on the left side, it only has black. And then on the right side, it has some mixture of black and purple. Now, among these 2 splits, which one do you think is better? Let me see. Anybody can help us figure this out. Among these 2 splits, is it the first one or the second one? Which one is better? Or at least somebody should give it a try. Okay, so there's some information in the chat. Okay. Somebody says the second one and has proceeded to say, please, I don't know why. Okay, and there's a contrary view, the first one. Please, the first one, maybe you know the why. Can you help us with the why? Or you also don't know why? Okay, let me leave you to answer that.
Please, I also don't know why.
You also don't know why. Okay. Okay. I think in about next week, I mean, yeah, this Saturday, the Saturday after this is going to be the general election. And I think some people are also going to vote. And up to now, they don't know why. So you are not alone. Okay, so Derry says, I think the first one. Okay, so please can you help us with the why?
I think it's the first one because when we check the other the subsets,
Okay.
it looks like there's no decision to be made.
Okay. Okay. All right.
I think it's
You're welcome. Okay, so Alice, in any case, it's going to be one of them. Okay. Now, the interesting thing is the best one, okay, based on what we have over here, is the second one. And I tell you why. It's the second one because at the end of the day, the decision, like Derek was trying to say, there's no decision to be made, okay? But that's actually what we want because we are trying to separate the black from the purple. So upon this plate, we're able to get a chunk of the black. So now we don't have to worry about this leave node again. We only have to concentrate about this. Now, the first one basically means that, okay, then this one is going to split again, and this one is also going to split again. So you can just look at the computation that needs to be done. Okay, both nodes are splitting, so there's going to be more computation. In the case of this second one, we can clearly see that, okay, because this has been completely separated and it is so unique, they are of the same class, there's no computation to be done on this particular node. Okay, so this now becomes a leaf node based on what we have over here. Then the algorithm or our computer resource only focus on the other node, so that imagine both hands are supposed to do some work and one is done with the work. You just rest that hand and concentrate on the other one with the other hand. if you go ahead doing the work simultaneously with both hands, you may get tired, basically. So at the end of the day, this is what we want, okay? Where we can split, and the more we degenerate into having nodes, we're able to split the data sets like that we get more leaf nodes and few computational nodes. At the end of the day, we want to get something which is separable. So at the end of the day, this is what we want. Sorry. No, this should be, okay, I think this is a repetition. Very good. So at the end of the day, this is what we want. And then what we have over here is something we want to maximize. Okay. So what we have here is something we want to maximize, and that's what we call the information gain. Because at the end of the day, see what's happening over here. We are gaining some information, okay? And there's a calculation which we are later on going to see. And the way we calculate information gain is by using entropy. Now let's go back to secondary school where we did a lot of entropy, okay? At least we all did science, so in physics and especially in chemistry, we dealt with entropy. Please, who can help us with a layman brief definition of what entropy is, so that at least we start from that base, okay? Something you already know, and we see how it applies over here. Entropy, okay, so there's a chat. Somebody is already choking somebody. Okay, so Sally is saying Mariama. Maybe Mariama can help us with entropy. Some of you even use it as your nicknames back in secondary school. Okay, Sharif, help us with entropy.
So please, what I know about entropy is that it is the measure of disorderliness.
Okay. All right, thank you very much. And there are a lot of synonyms that we can use, okay? So the disorderliness can be also known as the measure of impurity, okay? Good. So now clearly, okay, there's an answer in the chat. Okay, the measure of randomness, exactly. Good. So over here, we can clearly see that, okay, as far as the split over here is concerned, if you are to compare this with the previous split, okay, where we're trying to look at this, you realize that over here, there's a lot of randomness or disorderliness, like our brother rightly said, okay? Because at the end of the day, we want to split our data into black and purple. But because of what we see based on this split, there's still some entropy over here. We want to be clean as possible. And over here too, there's still entropy. But over here, you can see that based on this split, there's a lot of information gain over here. We are maximizing information gain. So the information we get over here is said that, okay, everything is black. That means there's less entropy over here, and at least there's a little bit more entropy here. And then, okay, very good. So Derek is also putting in the chat that entropy is the lack of uniformity. And I think that is an example or a definition that best fits in this particular scenario. Good. At least we all went to different secondary schools and we had different teachers, so different examples. But then the point is what we are making over here, that we are going to use entropy to calculate the information gain. And when we use entropy, we want to maximize the information gain. So if there is a lack of uniformity, which is entropy, and we want to reduce that one, then that means we want to have a lot more of uniformity. And that's why, or that's what makes this a better choice in terms of the splitting than the one we have to our right. Good. So now let me just go back to what I have over here. The slides are almost done. I think this is just about the last one. So at the end of the day, you want to maximize information gain. And I'll leave that to you. So the formula for calculating entropy is a very simple formula, okay? Oh, I think I should have brought it over here to make sense. But then it's nothing too different from what we learned from secondary school. Okay, so at the end of the day, an information gain of 1, okay, is good for us, and we'll be subtracting everything from 1 based on the entropy that we have, and we'll be getting that. So let me just quickly switch to what we have in here, where we are actually going to build some of these models ourselves. Okay, so now for today, at least with this introduction, and I'll highly recommend, based on the reference I have over here, please spend time to read some of these things over here, because it will help you understand the foundation. The point is, when you are building or when you are using these algorithms, you are not going to reinvent the wheel. The algorithms are there, you just plug and play, but you need to understand behind the scene, okay, this is what is being calculated, and that's what you need. So over here, we have that, okay, so classification algorithm is a technique that uses machine learning to categorize objects or data into groups based on their characteristics. So in here, we see that, okay, let me zoom in a little bit. We have data point over here. Now with this one, it's very simple. It is linearly separable. So over here with just this line, you can see that all the dots are what we have over here, and all the triangles are what we have under the bar. So this is class B and this is class A. And we want to find a way of maximizing this basically. So the objective of this is to understand the theoretical concept. At least we have some theoretical concepts of decision tree. So we are going to develop a decision tree classifier now. Hopefully on Friday and subsequent times, we look at the random forest. So the random forest is just an extension of the decision tree classifier. So the decision tree is just like one tree, and the random forest are multiple decision trees we put together to make the algorithm work. So this is what I just repeated in the slides, and this is also what we saw in the slides as well. All right, so these are some few application domains of the decision tree classifier in finance. Okay, so decision tree can be used for credit scoring, fraud detection. So whether something is, it is very good on binary classification when we just have to, even though it can be used for how do you call it, multi classification, but then it is very efficient with binary classification because of we trying to maximize the information gain, trying to reduce entropy. We don't want confusion in the splitting. That's basically the concept that decision tree brings on board. And also in business, decision tree can be used to analyze customer data and make market decision. So we want to know if something is going to sell, okay? A new product is going to sell. We have some data. We can put it in a decision tree algorithm, and it will minimize the entropy in the data set, and we'll be able to predict whether something is going to sell or not. Now in medicine, we can also use decision tree to build classification algorithm, and whether it is a cancer detection algorithm or maybe some disease classification, the features will come in, and this entropy thing we just spoke about will be calculated, and it is able to split the data sets into the perfect 2 classes that we may want to have. So over here, what I'm going to do is, let's quickly go into the code, okay? And what you are going to do is you are going to build a classifier based on some data set that we already know. And later on, I'm going to give you the opportunity to also explore with your own data set. So we are going to build 2 classifiers over here, and we are going to do some analysis of these classifiers. Now, the first one we are going to build is we are going to use the data set you already know, which is the IRIS data set. And I like using that because we've already done the analysis of it. So at least with that data set, we have it at our fingertips, okay? We just want to see how the algorithm will work around it and how it will be able to make that prediction. And what I would prefer you do is, okay, so you build this, then we go back and go and take the one we built with the neural network. And of course, we can do some analysis, which one was performing better and things of the kind. And that's basically what we do when we are doing some academic research, okay? Because it is never going to be a one-size-fits-all where one algorithm is going to solve all your problems. No, other algorithms are going to outperform some. So you try and build as many as possible, and you do the analysis thereof. So with the Iris data set, we can get it from scikit-learn, and we can also get the decision tree classifier from scikit-learn. So remember, scikit-learn is a very big library, has a lot of things in there, and we can use them as and when they need be. So I'm going to say import sklearn, this from scikit-learn, and let me be more specific over here. So I'm going to say from sklearn.tree, I'm going to say import decision tree classifier this way. Now I'm going to say from sklearn.data set import what we know already, load Iris. So I'll run this, and I hope you don't have any problem. Okay, so this cell is complete in terms of the running, and we don't have any problem. So let's load our data set, and we know what to do. So I can say the data is going to be this load data set, and I'll just call it up this way. And now we have our data set that we can work with. So I'll do a Control-C, Control-V over here and run this to have a preview of it. We already know what these ones means, okay? The Iris setosa, the sepal length, sepal width, petal length, petal width, blah, 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 okay? And we have them listed out over here. And we also have the targets. And over here, it has already been converted into zeros and ones for us, so you don't have to worry so much about doing the label encoding. All right. So this is what we want to use to build that algorithm, to build that model. And later on, this decision tree classifier that we have from scikit-learn, okay? Well, yes, I think this one, yes, it will help us. Okay, this one will help us kind of have a visual representation of that decision tree that will be formed behind the scene and the calculations. So we are going to see all that. But then let's concentrate now on the data that we have. So this is the data, and now we want to split it into our X and Y. So this one is very simple. Now when I do X inputs, it's going to be equal to the data dot, and Sheriff asked the last time, there's a dictionary and you have data as the key over here. So I just want to grab this to get the X input, and then the Y input is definitely going to be the target as we have over here. So data.data is going to give me the X inputs, okay? So I'll run this, and now I have just that portion of the data set, okay? Then I'll proceed to have the Y output. So the Y output is also going to be data.target. And let's do a preview of this. And indeed, we have the target showing up over here. And these are the things we need to build our model. So once we have our inputs and our outputs, we can put it in the classifier to get some model built for us. So over here, we can instantiate the model. So the model is going to be equal to, remember, we've already imported this decision tree classifier over here. So I can just bring it down. So the model is going to be equal to this, and I'll just instantiate this. Now this looks familiar with some of the things we've already done. Remember, even last week when we took the trouble of writing our own code, okay, for the perceptron, we kind of modeled it this way. So whenever we do this, yes, we have the skeleton of the algorithm, and we have it saved in a variable called model. So now I can do model.fit. And what do I want to fit? I want to fit my X and my Y. So I want to fit X underscore inputs, then Y underscore outputs. That's basically that. So I ran this, and we don't seem to have any problem. The model is built, okay? So now that the model is built, you can see that it was very quick, okay? We can do some prediction. So now when I do model.predict, I can now pass in some data over here to make some prediction. All right. Now let's look at something like this, okay? the last one we have over here. Remember this one, we didn't split into the 10%, sorry, the 80-20 rule, okay? We could have done that to be doing the splitting and also doing that, but then this is just for us to quickly build the model and see how simple this is. All right, so now that we have the model, we can do a prediction, okay? And over here, I'm going to pick the last data point we have over here. And basically, this is going to give us a class of 2 because this is the last one, and the last we have over here corresponds to this, which is 2. So when I come in here and now, put this over here and now run this, we definitely get a class of 2 over here. And we know what 2 is. Based on the data that we have, we know that the counting starts from 0. So Iris Setosa is 0, Versicolor is 1, and then Virginica is 2. So basically, it is telling us, given or based on the model that we have built, given the data points, what we have over here, it is going to make this prediction for us. Okay. Now, let me just quickly walk you through the diagram, because the diagram will also help us understand a few things that are working behind the scenes. So what I'm going to do is I'm going to say from sklearn import tree, and I'm doing this. Remember, I've already imported from sklearn.trees import decision tree classifier. So I was very specific, but then I just want to have tree to do certain things. That's why I'm running it again. So now this is what I want. I want tree dot there's a method over here called plot tree. Okay, so I want to plot the tree. So I'm doing tree.plot tree or plot underscore tree, and then I pass in the name of the model that I want to plot. So remember, the name of this model is model, and it is from this decision tree classifier. I fitted it with some data, X and Y. I'm done some prediction, and I want to see how the tree looks like. So when I run this, it will take a while. Now we have this. Now I will beg you, like, you look at this objectively. Okay, very well. Now over here it gives us some information, okay, and the information it gives us, we cannot really see properly based on how this is structured, okay, but then it is contained in the boxes we see over here. So here we see the splitting. So look at this. Based on what we know, okay, we know that the data set that we have had 3 classes. So Iris, Setosa, Versicolor, and Virginica, and they all had 50 data points. All right. So now upon the first split, it was able to split the first one, all the 50, but into 1. And then the rest was 0, 0. So now this then becomes a leaf node. There's no confusion over here. There's no lack of uniformity. So we don't have to further on split this one again. But then the other splits, clearly you could see that because this 50 has already gone into this, we see that, okay, this one, so you could see that the sample over here is 100 because it contained the other 2 data points over here, or the other 2 classes, basically. So this one does the splitting. Now, clearly you could see that when it's splitted over here, it is not too clear, but then we can see that, okay, over here we had 49. The original was 50, but it was able to split 49 over here, and it was able to split 1 over here. So there was some level of impurity based on our understanding, okay, that's gone over here. But over here, it was 49. And then the other point, or the other part too, it was able to split 45 over here. And then I believe 5 was left here. Then it goes through the splitting again. Now over here, it went through the end. Like I said, it is basically checking how impure other data points are inside of the mix. So over here, we can clearly see that over here, this is a root node. Over here, everything was 50, 50, 50. It split, and it was able to get a very clean swipe over here. So over here, the first 50 was able to group correctly. So there was no need for further splitting over here. But then it concentrated on the other ones that were still mixing up. And we could clearly see that we also have the rules. Okay, so you could see that the rules over here is saying that it's not too clear, but then clearly you could see that the x3, okay, is less than negative 0.8, okay, and the Gini is basically the level of impurity we have over here. And I don't know if I'm seeing this very well. I believe it should be 0.667, okay, so approximately 0.7. So you could clearly see that there was some level of impurity over here, about 70%. Then it needed, so this was the original one, okay, very good. Now it came here, the Gini had dropped, the impurity had dropped to about 50%. So clearly you could see that half of the work has been done over here. So we're left with this one. It further went down over here because clearly we're getting rid of almost everything over here. We're just left with one. It eventually went down, and the moment is, if we still have something to split, it will continuously split until we have nothing to split. And over here, it went down to a point that, okay, over here we have nothing to split. So we have 0 over here, we have 2, which is just this class, and we have the other one 0. In this case, too, we have 0, 0, and then we have just 1 over here. And you can clearly check that for all the leaf nodes, we just have everything into one class. For all the leaf nodes, for all the computational nodes, there were other things mixed up, and we needed to do further computations on them. So I believe this one will bring finality to why, when we have some uniformity, when we have less entropy, less confusion, less uncertainty in a particular cluster, it helps us, because then we are definitely going to reduce on the computation. So this is basically how the how do you call it, the decision tree classifier will handle things. Please, are there any questions before we move on to the next thing briefly? Okay, so I believe the silence means consent. So let me just quickly move on to other things. So like I did indicate, what I want you to do, okay, when you have this, just build the, how do you call it? The one we built with the neural networks, and do the comparison. And we are definitely going to see some differences over here. Now, in addition to we making predictions, we can actually do a prediction of the probability distribution, okay? And that's what initially the neural networks were giving us. So let me just come down here, still copy this, okay? This one was giving us a class of 2. All right, so now I run this, and now I just don't want to predict, but I want to do a prediction of the probability distribution. So this is what we have, this method. So I'm saying that model.predict underscore prob A. This is a probability distribution of the data points we have over here. And when I run this, we see something interesting over here. So over here, it is giving us the probability distribution of all the classes. And this can come in very handy, because if we are working with some data points, okay, now let's look at the definition of what we have over here. The definition of what we have here, based on the probability distribution, is this is 0%, this is 0%, and this is 100%. So it's telling us that it is 100% sure that this data point will belong to that class 2, because it will start counting from 0, 1, 2. But in some instances, we may have, let's say, it's giving us a probability distribution of maybe 51%, and another one is 30-something%, and another one is 1%. Imagine if this was a disease classification algorithm, we'd want to further go into details and know exactly why certain things are happening. There could be an instance where in some disease classification, there could be comorbidities, okay? So the person is not just exhibiting, let's say, just malaria, but maybe there's malaria, there's typhoid there, and there are other diseases there. So it will pick up all those features from the data you fed the algorithm with, and it will be able to make that concrete prediction for you. But that will be for you, the machine learning engineer, to understand your numbers and also present it to the medical expert that, oh, we are getting about 30% typhoid, okay, about 20% malaria, and maybe after about whatever percent something. And it will surprise you to know that the medical expert will look at them and be like, yes, this was exactly what we were expecting based on their understanding of that particular area. Okay, so this is also for you to understand the probability distribution. And once again, like I said, when you build, and I believe you already have the neural network model over there, so just run this one on two separate how do you call it, notebook files, and just do the comparison, which one is giving more more certainty in terms of your how do you call it, your performance, one way or the other. All right, so like I said, okay, there's a question in the chat. Okay, so it says, sir, please, what does the xt, okay, less than or equal to 0.8 mean? All right, so these are basically the computations, okay. These are basically the computations that were derived from, so over here, the key things we are calculating is information gain and then the entropy. So the X, whatever, is the information gain, and the Gini is the level of uncertainty or the entropy in there. So with the question that we are asking, the information gain of, at the end of the day, an information gain of 1 is perfect. That's 100%. That means we have a lot of information in there. Basically that. And then the Gini is also trying to no, I don't think so. The information gain of let me see. Okay, yeah. So the information gain is what we have over here. And because I'm seeing some interesting things over here. So over here, we see that yes, the information gain, I don't know if you picked it from this one. Okay, that's what we see over here. And the uncertainty is what we see over here. That's the calculation. Over here, you can see that. Okay. Over here, clearly you can see that the Gini, because this was able to split, this is a leaf node. You see that the Gini, or the level of uncertainty, or the entropy, now goes to 0. Now this one, there's no lack of ambiguity. Sorry, there's no ambiguity over here. So the Gini is basically telling us the, I mean, how do you call it? The entropy. Okay. So there's a calculation if you are trying to do this by hand called the Gini index, which is a simple calculation. You just need to calculate basically that. But then the algorithm behind the scene works everything out for you. So the lower the Gini index, the better for us. But you can see that for every leaf node, for instance, this is a leaf node. You see that the Gini is 0, perfect. This is another leaf node. The Gini is 0, perfect. Another leaf node, there's no breaking down over here. The Gini or the entropy is 0. But then this was a computational node, and there was definitely some level of uncertainty about 0.4 for over here. And then some calculations needed to be done before we could move on. Now, what I'm also picking up, okay, not entirely so. Okay, not entirely so. So at the end of the day, the X, what we see over here is the information gain, and this is the level of uncertainty, which is the entropy. And you realize that the lower the Gini, the higher the information gain. Okay, the lower, because over here it was clearly 0. Over here we are satisfied. Okay, but over here you can clearly see that in this particular instance there was some level of uncertainty, some entropy, but it was minute, it was small. Because if we are to even look at the data points or the breakings as we have over here, it was only one of the other class that was mixing up with the entire 47 of the other class. So you could see that this is a 0.0, very, 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 very low. So the entropy was very low. But then upon doing that computation again, that iteration of splitting things back and forth, we realize that, okay, now both nodes are now 0, 0 in terms of the entropy. All right. So the X, whatever thing you see over there, is the information gain. And I believe I should have spent a little bit time on the manual calculation, except that, like Dr. Mills always say, whenever there is some manual calculation, then there's always some level of discomfort for some students. But at the end of the day, I think these are the things we are seeing from the, in the diagram, basically. I believe these are the things we are seeing from the diagram. So the first one we have over here is, I believe this would be the, I don't know. Let me see, 0.5. Okay, so this one was, okay, so this one was the first one, okay? The mother node, okay, or the root node, where the number of samples we had over here was, we had 50, okay, 50 and then 50. And then I believe this was the information gain, no, sorry, the information gain we see over here, and then the Gini of a 0.667. Okay, yeah, I think that's exactly what we see over here. All right, good. So that was the information over here. And we have a 0.5. I don't know where this is coming from, but definitely some parameters were used in there. Now, it was able to break this down to, I believe, these two. If we can just bear with me, okay? And over here, we have this. And then the Gini over here, remember, upon breaking this one down, this one was 0 because we were able to properly classify that particular group all at once. So we see this over here. Now, what this one also does for you in terms of your analysis of things, okay, is that you could clearly see that the first class didn't have a lot of issues splitting. The first class don't have a lot of issues splitting. And I don't know if you remember very well, when we did the pair plot of the this particular data set, do you remember we saw something interesting over there? How many of you remember? Okay, let me see if I can get that one over here quickly. So let's say we have what do I even want? I want okay, from import Seaborn as SNS and SNS dot pair plots, and we need the data. The data. Okay, so let me just work out on this briefly. So the data is going to be X inputs, and then Y input, but I need to merge them. So let me also import pandas. So import pandas as PD, and then let's do PD dot I'm looking for something like merge. Okay, so there's a merge over here, and I want to merge X inputs and then the Y output. I don't know if this is going to work. It says can only merge series. Class numpy array was passed. Okay, so we can only merge a series or a data frame. Okay, so let me just convert everything to numpy array. Sorry. So let me do X is going to be equal to PD dot data frame this way. And now let me just pass in X inputs. Okay, so now let me just do a preview of this. Okay, everything looks good. And now let me do same for Y as well. No, the y. The y. Okay, let me try that and see. So y is going to be equal to this, and let's do y output. Okay, so let's see y. All right. So now let's do pd dot merge, and now let's do x and y. Oh, assembly. Let me see. Okay, let's do concatency. So pd dot concat, and let's do x and y. Takes one positional argument, but 2 was given. But I want to concatenate. Let me see. This is even worse. First argument must be iterable. Okay. Okay, let me just do it this way and see. Okay, so SNS dots per plots. Let me pass in x over here. Okay, so I don't know if we cannot see this properly because we cannot get the hues. Okay, we cannot, the way the data set is structured. If we can, okay, let me just, I think I should have it somewhere there. That's data sets. Let me see this one. Okay, yes, I have the iris data set over. So let me just grab this one and work with this. So Control C, let me bring this up over here. Okay. So now let's do new data is going to be equal to pd dot read underscore CSV, and then let's have iris dot CSV. Okay, so now let's do a preview of this and see exactly what we have. Okay, so this is what we want. Let me drop the IDs. Okay, I can even make it work. So let's do SNS dot per plot, and then let's pass the new data over here. Okay, so it is basically going to give us the same plots, but then what we are interested in is making sure that we get a hue based on the species. Okay, that's what we are not getting from the other one because of the way the data was structured, and I was finding difficulties in merging them. So the hue is going to be equal to species, and then we are going to see the colorization or the distinction based on the species or the class. Okay, so that is what we are going to have over here, and we see that all the iris setosus are the blue ones, the iris vesicular are the orange ones, and the iris virginica are the green ones. Okay, so this one was class 0, class 1, and class 2 in that 0-1 classes that we had. Now we clearly are seeing that upon the first plate, okay, upon the first plate, everything from class 0 was correctly splitted. We didn't have any entropy over here. The Gini was 0. And over here, we had 0, 0 over here. It wasn't mixing up with anything. Then these ones were a little bit behaving funny. Those were the class 1 and then the class 2. Then it further went on to split them. It was able to split a lot of the class 1, but then a little bit of the class 2 was still entangling about 5 of them. This one too had some mix over here. It went further on and on and on and on. So clearly we can be very confident about the first class, which is the iris setosa, okay? And that's exactly what we see over here, because remember what I told you, that with the iris setosa, which are the blue ones, they are almost separable from the other groups, okay? If you have to look at the blue ones over here, you can see that here, they are very close to each other. Here, you can see that there's an entanglement between the orange ones and the green ones. So chances of misclassifying or the calculating the entropy, the level of uncertainty based on even what we just saw from our illustrations over here, okay, in terms of things being mixed up, we are clearly seeing a replica of it over here. But then upon the first split, this one will clearly split all 50. But then these ones will split and some will go into the other one and others will go into the other one. Then we'll refine or we'll break into other, how do you call it? Other computational nodes to also do the computation based on the entropy, do the calculation, and now split again. And it can go on and on and on. So clearly you could see that with the Iris Setosa, we don't have so much problem. And this is where visualization can also help you a lot. So maybe there's some data you are trying to explain why certain things are happening and why you don't have so much problem with a particular class, but then some other classes are giving you a lot of problem. These are things you can do. So clearly, once you see these, you know that, okay, some of them are linearly separable, others have a lot of data points mixed up or intertwined. So we need to perform a lot more computation. But then the beauty about decision tree is you just build it, okay? You don't have to worry so much about how the computation is done, how calculations are done. The algorithm has already been developed and it has been optimized in a lot of ways. There are a few ways that we can also change some parameters, which we are going to look at. But then for now, I think this should be okay for us in terms of we getting the fundamental understanding of decision tree algorithms. Please, are there any questions? Okay, Mariama, I can see your hand up. Please, your question.
Please, so I wanted to ask that when we're trying to predict so we used one of the input data to the prediction, and then we got to, and then when we use the probability to check the probabilities for each of the classes, we realized that the last one was 1, and then the first two were all 0. Yeah. So I wanted to know that, is it that always we'll have one of them being 1 and the rest being 0, or there can be different like instances? And then if it's always 1 and then 0, 0, does it mean that it's because of how the decision tree works, like it's trying to make sure that it groups them without like mixing with the other classes, or what?
Okay.
Please, that's my question. I hope you get it.
Yes, please. I got your question. So
Thank you.
let me try and respond to that. And this came about because of the probability distribution. Okay, very good. Now, once again, this data set, okay, is not going to give us a lot of problem. Now, this 0, 0, and 1 we see over here are basically in percentages, okay? So this is a 0%, this is a 0%, and this is 100%. So the probability distribution is telling you that, okay, when we just did the prediction, it told us 2. We know that this is 0, 1, 2. So we knew that, okay, it was of the third class. Is that okay? But then the counting starts from 0. It was of the third class. Now, what this probability distribution is telling us that it's 100% sure that this is of the set. But then there are instances where we are definitely going to get maybe a 0.3 over here, which is going to be a 30%, and maybe a 0.7 over here, which is going to be 70%. But at the end of the day, when you do model.predict, it is going to tell you 2, because 70% is bigger than 30%. No two ways about that. And the reason why I brought this up is sometimes just giving us that, oh, it is of this particular class may not be good enough. We want to get to know the nuances between some predictions, okay, or get details into some prediction, because the example I was trying to cite is when we are using machine learning in in building biomedical applications and predicting diseases and stuff like that. Okay, there could be comorbidities where one person is suffering from malaria and also typhoid, and maybe a little bit of cholera. Is that okay? Now, let's assume this class is malaria, this class is typhoid, and this class is the other one I mentioned, malaria, typhoid, and cholera. Okay, good. So this is malaria, typhoid, and cholera. So currently we can confidently say that the person suffering from this disease has cholera. Okay, let me do it over here. So the first one is malaria. The second one is I think I always get this one wrong. Is it cholera or cholera?
Cholera.
It's correct.
Okay. And then the typhoid. How do you spell this? Is it this? Is it spelled this way, typhoid?
Yeah.
Okay, thank
Yes.
you. All right, so we are seeing that the first class we are assuming is malaria, second class is cholera, and then the third class is typhoid. All right, now let's assume the prediction came, okay? And at the end of the day, everything is going to sum up to 100%. So here it was 0 plus 100, definitely 100%. But let's say the person has, based on whatever thing we saw from our model, the person had about 10% showing as malaria, okay, which is going to over there show as 0.1. Then the cholera is about 0.4, and then obviously the typhoid is about a 0.5. All right, at the end of the day, everything sums up to the 100. Now what happens is when we just do model.predict, it is going to predict 2 because this is the one with the highest probability. Okay, even if it is, let's say 0.49 and this one was 0.48, okay, very close, it is still going to predict as typhoid being the class. But then imagine we have this and we have built a model. Beyond predicting that, oh, the person has typhoid, we would also want to present this granular data to the medical expert that, well, even though our model says the person has typhoid, also you should be checking for cholera because they are very close. So that's the point I was making over here. So the probability distribution is always going to sum up to 100%. But then this one clearly tells us that it is 100% sure that this is of this particular class. And we can, I mean, it's justifiably so because this was a data set we used all to train. And we are just using one of it to predict. So definitely the model or the classifier has seen that data before. So it is able to know that, oh, this data there, I know this data. So it is 100%. But in some instances, we may get, let me try and see some instances that, and we can only do so by looking at this variable. So let's say, let's pick up some data points, okay? Let's say if we pick up something around this region for sepal length, okay? So sepal length, let me pick something around 6.2 for sepal length, okay? Sepal length is 6.2. And this one is sepal width. Sepal width, let me pick, let me see this number. Let me do a 3, let's say a 2.8, okay? So sepal length, 6.2, sepal width, let me just type them over here. Sepal length, okay, we are doing a 6.2, and then the sepal width, we are going to do a 3 points. Let me see. Sepal width, a 2.8. Let's do 2.8. And we are picking these numbers strategically because we have a lot of them mixing up over here. So it is definitely not probably not going to give us 100% of a particular class, and that's what I want to prove over here. So let's also pick some values for the other ones, the petal length and the petal width. So petal length, let me see, petal length and petal width. So let's do a 4.5 over here, petal length. So petal length, let's do a 4.5. Okay, there's somewhere here. So 4.5. And then the petal width, let's do a 1.7. A 1.7. So the petal width. So petal width, let's do a 1.7. Okay, so now based on this, let's do the calculation. And let me just find out, because the order also matters, okay? So the order is as we have it over here. So the order is what you see over here. So the sepal length will come first and blah, blah, blah. Okay, so now let's do model dot predict underscore probability, okay, or prob A. And let's put out these values over here. So the sepal length, we are seeing a 6.2. And the sepal width, we are seeing a 2.8. And the petal length, we are seeing a 4.5. And the petal width, we are seeing a 1.7. Okay, so based on just eyeballing on this, when I run this, okay, we are still getting a probability of this class very high. Let me see. That's going to be the last class, which is the green. Okay, so I wish we had something that was sepal length. Okay, let me try and change some parameters over here and see if we can get something a little bit different. Okay, this one has just changed the class. I just want the probability to shift a little bit and see if we can get a splitting of probabilities. But then it appears all of them are not really giving us anything. Okay. All right. Unfortunately, I'm unable to show this, but then I'll find some other data sets. We are going to build other models, and we are going to see that, okay, it is not always the case that you're always going to have a 1 and a 0, 0. There are instances where there's going to be some splits, and that split will be as a result of the model not being too sure, okay, of where it actually lies. And it is indeed possible, because you see, at the end of the day, what actually happens with, let me just show you, what actually happens with these whole calculations is there's a high chance of something going wrong at the end of the day. No two ways about that, okay? These are machines and algorithms working. So even though it can be very sure that, oh, this one I'm sure, the splitting the Gini is 0, but then maybe inherently or how it reflects in the real world is a little bit different. So those things are possible at the end of the day. All right, please, I hope your question is answered.
Yes, please. Thank you.
You are welcome. Please, any other question? Okay. So if there are no questions, I think we don't want to bombard you with a lot of things. Clearly see from our schedule, there are lots of things to cover. So at least we have the theoretical understanding of this whole decision tree, okay? And I said the random forest is just an extension of it. So just one tree, we are just multiplying the number of trees we have to get a forest. And if your guess is as good as mine, if the tree is probably doing a good work, it basically means that the forest might do a better work, because the forest will have a lot of trees working on the problem. But then there's always a trade-off, because you also don't want to have models that are computationally expensive in their running, okay? Some models will run forever. You don't want to have that. Imagine a tree, if for instance, maybe the tree is taking like, let's say 5 minutes to run, and you have a random forest of 10 trees, you can just do an extrapolation and know how complex that structure is going to look like. But at the end of the day, the random forest is also there. Some most literature in terms of these machine learning algorithms will suggest that, okay, if decision tree is giving you some good results, then try random forest to actually check if you can get better results, because most likely you can get better results from there. So those are how some of these algorithms are interrelated. And then moving on, we are going to look at support vector machines, the naive Bayes, and the KNN algorithms before we move on to regression. And remember, with regression, we're also going to come back to this classification, how do you call it? Decision tree, because we can also use decision tree for regression as well. All right, please, any other questions? All right, so if there are no questions, I think we can end here. We've covered a lot from the theoretical concept to the mathematical foundation to actually building some of these models. And we don't have to reinvent the wheel. The algorithms are there. We just have to understand the concept behind them, some numbers that may appear when we are building them, and how we can optimize them if some things are not going right. All right. So we'll end here. The videos will be available. So from now till Friday, you can watch it, play it back, look out for your own examples and see how you can also work with this. Okay, so we will end here and we'll meet, God willing, Friday. Okay, so have a good night and we meet on Friday.